Hello students, in today's class we are going to discuss about some questions based on circular motion and friction. So firstly we will go through some very basic ideas related to circular motion, and then we will start solving problems, and then we will take two examples where these basic concepts are applied. Let's begin. So the acceleration of any particle following a circular path can be resolved into two components, radial and tangential. So if there is a particle moving in a circular path and if it has some velocity here, some speed, you can say velocity is directed along the tangent, then with respect to center, if we join a line that goes outward, this is called the radial direction. And the tangential direction is along the tangent drawn to the circle, at the point where the particle is present. Now the particle, if it has to follow a circular trajectory, it must have a radial acceleration. Now this radial acceleration must always be towards the center, and that has a formula: a radial is equal to v square upon r. Now see, the direction has not been mentioned here. Direction is always towards the center, and there may be one more acceleration, the other component, which is along the tangent, maybe in the direction of velocity or opposite to velocity, but that component has a magnitude same as rate of change in speed. So I am saying modulus dv by dt, where v is the speed. So only the magnitude. If speed is increasing, that means a tangential and velocity vector are in same direction. If speed is decreasing, then directions are opposite. Nevertheless, in both the cases, the radial acceleration is always towards the center. So this is the basic idea that we are going to utilize to solve the problems in the further slides. Let's begin with the first example. To whirl a stone tied to a cord, one has to move the free end of the cord on a circular path, pulling the stone on a larger circular path. So we have a stone here, and we are having a string whose length you can say is L, and we are pulling this stone with the help of the other end. The other end is being whirled on a circle of radius small r, and the stone is whirled, or stone moves in a circle of radius capital R. Length of the string is small l. The question is to find out the resistance. See here, as you can see, at sufficiently great speed, tensile force in the cord becomes so large that effect of gravity can be neglected. That is, as you keep whirling around, the string becomes almost horizontal, which we have all experienced. We must have done all those things in schools, so where we just keep whirling a stone or a bottle tight to a knot, etc., and that performs circular motion. Initially when the speed is small, the path is circle and the string makes a cone, but if we increase the speed, we see the radius of the circle keeps increasing until it appears to be a horizontal circle. Alright, so that's exactly what is being said. So at this speed, when the string almost becomes horizontal, air resistance, but at this high speed, the air resistance becomes quite significant. Before we start solving this problem, let us first try to label out few things which can be utilized a bit later, while writing the equations. So let us say the stone moves with a speed u, the angle here, let us say, is theta, and angle on this side, let us say, is phi. Okay, so this angle will be 90 degree, okay, as the say other end moves on a circular path. So the radial and tangential directions make an angle 90 degree. If we extend this line, okay, we see this angle is theta, this is phi. So this angle particularly will be the exterior angle of the triangle found by small r, L and capital R. So this will be theta plus phi. Okay, so obviously this angle is 90 minus, okay, theta plus phi. Okay, in a similar way, this angle would be 90 minus phi. Okay, all right. So we have say a few more equations coming up. Okay, if we have a triangle, then obviously we can write the triangle law. Okay, so we can write L upon sine theta is equal to R upon sine of theta plus phi is equal to small r upon sine phi. Okay, so this gives say us the relation between the three sides of the triangle L, small r, capital R. Okay, now let us start with the dynamics. Say tension in the string is T. Okay, tension in the string is T. Okay, so T sine phi must balance the resistance force. Okay, and T cos phi gives us the centripetal acceleration or the radial acceleration. So m into u square upon r. All right. Now from the constraint, that is, the string has to remain fixed in length. Okay, we can say v cos 90 minus theta plus phi, which is v sine of theta plus phi, that is equal to u sine phi. Okay, so from this we can see u is equal to v multiplied by sine of theta plus phi upon say sine phi. Okay, so sine of theta plus phi divided by sine phi can be found from this equation. We can see that is capital R upon small r. So we can substitute and say v capital R upon small r basically is going to become u. All right. So substituting, we can find out the value of mu square by r. But if I divide these two equations, okay, if I divide these two equations, then in that case we can say tan phi, or simply f is equal to mu square upon r multiplied by tan phi. Okay, so we have say a variable left, which is tan phi. We can substitute the value of u square. Substituting, we get mv square, okay, capital R upon small r. Okay, after substituting the value of u square, we get this value. Tan phi, we can say, is say square root of cos square phi minus 1. Okay, so how exactly will we find the value of cos phi? Now again we can use the triangle law. Okay, cosine rule gives me the value of cos phi as L square plus R square minus small r square divided by 2LR. So if we substitute that, here it should be secant square, not cos square. So we have mv square r upon small r square, okay, small r square, it should be here, square root of, now for the secant square value we can say it should be 2 times L capital R divided by r square plus L square minus small r square whole square minus 1. Alright, so this is the, say, substitute for the secant square phi. Cos square phi or cos phi can be found as L square plus R square minus small r square divided by 2 times LR. Okay, so taking the reciprocal, we have the secant phi, and substituting, we get the value of the resistance force for this problem. Okay, so the next example is here. A particle is placed on a rough horizontal ground and is made to move in a circular path of radius r. The coefficient of static friction between the particle and the ground is mu. The particle starts from rest and its speed increases gradually until it reaches the limiting speed at which it is about to slip. The particle takes the minimum possible time to reach this limiting speed without slipping. Find the distance covered by the particle in this duration. Alright, so there are a few things which are very, very important. It takes the minimum possible time. So if the particle is taking the minimum possible time, they mean to say it is always having the greatest possible acceleration it can. So the greatest possible acceleration A should be equal to mu g. Okay, for no slipping, the acceleration cannot be more than mu g. Alright, okay, so the particle is also following a circular path. Okay, let us say it is moving along a circular path of radius r. Then we don't know what is the direction of the acceleration, so let it be A here. Okay, and let us say in this direction it is having some speed v and it has a radial acceleration and tangential acceleration given as at. Okay, and in this direction a radial ar. If we assume this angle is theta, then we can say a cos theta is equal to a radial, which is v square upon r, and a sin theta is equal to a tangential. Now a tangential is the rate of change in speed, so we can express it as v dv upon ds. Okay, where we can say s is the distance it covers on the circular path. Okay, so looking at this, if we square and add, we can say a square is equal to v square upon r whole square plus v dv upon ds whole square, and this a is equal to mu g, so mu g whole square. Alright, so we can write then v dv by ds is equal to under root of mu g whole square minus v square upon r whole square, or in this case we can say ds, okay, is equal to v dv upon square root mu g whole square minus v square upon r whole square. And if we integrate on both sides, okay, so we can say it starts from 0 distance and has a maximum distance of s until the time it achieves the maximum possible safe speed on circle, and its speed must change from 0 to a safe speed which is root of mu g r. Alright, so now to integrate this, say, value that we have, okay, we can take v square upon r as some z, okay, so that we have v dv is equal to r upon 2 dz, okay, and integrate. Okay, so that function becomes integral, okay, r upon 2, okay, r upon 2 multiplied by dz upon square root of mu g whole square minus z square, okay, and you have 0 to, say, how much, 0 to mu g. Okay, so as we substitute the value of, say, v as mu gr. So mu gr upon r gives you z as mu g. This integral is sin inverse of x upon a gives you r upon 2 multiplied by pi upon 2. So the distance covered you can say is pi r upon 4. Okay. So the particle covers a distance of pi r by 4 until the time it reaches the safe speed on the circular path. Alright. So these are the two examples that we have discussed, okay, for an understanding of how to use the concepts of circular motion along with friction. Okay. I hope the concepts were well understood. Keep practicing. Thank you.